That means, first of all, am I sharing? Yes. Yes, Lara, is everything okay? You can just confirm, because I believe, yes, okay, thank you. I believe I can see my screen. Okay, that means volumes. Let's say normally we have no problem to calculate the volume, and I believe everybody has this intuitive idea how to calculate the volume of, for instance, of the cylinder, and especially the right cylinder. Okay, let's just quickly review the right cylinder. And when we actually say the cylinder, we're probably thinking about the circular cylinder. Yeah, and it's okay, but based on the definition, we can also see different shapes. That's what we need in order to say that that solid, that shape is a cylinder. We need two bases. Right? That we can see this shape is a circle, but it's a bottom and the top. Parallel and congruent. Congruent means identical. That's we have two bases. Let's look at this one. This is the bottom one, this is the top one. Also identical and also parallel. Even if we take the normal rectangular box, the bottom one and the top one. Yes, they are parallel and identical, congruent. That's the base. And now, if we have these bases, then the sides are connecting these two bases are perpendicular to the base, to the let's say XY plane. Okay, that's we can see we have two bases, and the sides, they create a right angle between the base and the side wall. That means this is the cylinder. We always have the base and the sides. I can say height. And now, in order to get the volume of any cylinder, we just have to find the area of the base times the height. Yes, volume of the cylinder is the area of the base and times the height. And we can see pi r squared times height. That's the volume of a circular cylinder. Length times width is the area of the base of a rectangular box, and the height, which we say automatically length times width times height. But it's definitely fit to that definition, yes, to that formula. And then let's say any shape, like of the base, we can say area of the base times the height. That means when we have this shape, this solid, like a right cylinder, we have no problem to calculate the volume. What is important? Important is to have, again, these two bases, and that side must be perpendicular. Okay, straight line and perpendicular, straight line and perpendicular. Where else? Here, and then perpendicular to the base. Oh, okay, you can see my drawing. Okay, that's what we will look. We will look at some shapes that they are not exactly cylinder. They have kind of like irregular shapes. We will try to use a cylinder to approximate the other shapes by looking at these shapes as a cylinder. Okay, that means let's see this. Oh, that means, for instance, that beautiful shape. We can see it's definitely not a cylinder. Looks like a little bit like football. Yeah, I think. Okay, that's what we have, what we see. Of course, we have to have some labels, some reference points, some notations. That's when we see this shape, which is placed in the XY plane, and it's like the beginning, the initial point is A, at the end, the terminal point is B. That means from A to B, and yeah, something like this. But now, what we will try, in order to get the volume, yes, we will try to approximate by a cylinder, because we can say it's not a cylinder. Maybe I can see that base and this one, if we will take that shape and put in the vertical position, we will see the identical bases, but the sides are not perpendicular. We can see we have that angle, we have that bend. That's what we will do. We will try to take that shape and cut. Okay, that means we will take a plane which is perpendicular to the X, and we will try to make like slices. we can kind of imagine like a loaf of bread and we're slicing. Okay, that's when we're slicing, and each of the slides, yeah, that's what you can see. This is that slide. Each of the slide will have a thickness and will have a certain base area, the bottom and the top. Okay, that's what we can think. We can think that each slide, each slab of that slice of bread, when we put flat on the plane, on the plate, we can think that this is a cylinder. Okay? With the area of the base and the thickness will be the height. I know that we still have like a curve, yes, that thickness of that slice of the bread has the curve, but we may estimate that this is like a straight line perpendicular to the plate. Okay, and now when we will get the volume of this one slice, one slab, then we can take the volume of each of them, add together, and then we will have the volume of the solid. Okay, that's, let me just write maybe here, volume of this one slice of the bread or one slab of that football. Yes, we need the area of the base and we need height. Area of the base. Of course, the base has really weird shape. Yes, we don't know, but let's wait. Maybe we will have a little bit more friendly shape, but we definitely can find the area of the base. And height, we will call that thickness, and this is delta x. We remember when we slicing, that was the definition of the integral, how to approximate the area under the curve. We were slicing, creating like the stripes, and from each stripe we were creating rectangles. But the base or the width of each stripe was we call delta x. The same here. We will be like slicing a little bit. Let's make it a little bit like 3D. Yes. And we will have each, I'm not good, I have on the other slide. We will slice and the width will be called delta x, which is the thickness, or if we put horizontally, it will be the height. Okay, that's me. Now let's look at this. Too fast. That's mean the same thing. Yes, the same thing, but we need the area of the cross-sectional part, cross-sectional region, we can see. Yeah, that perpendicular plane is cutting. We see, like when we cut, actually, I even typed this, yeah, slicing loaf of the bread. We slicing and we will see that cross-sectional area. We need this and we need the thickness. Right? That will be the area of, I mean, that will be the volume of that slice. Okay, let's look at this. That's my formulas. Okay, that's mean volume of one slide. We can see this as a cylinder, area of the base times height. And area of the base, because we can see each of the slide, for instance, 1, 2, 3, 4, 5, 6, 7, 8. We have only 8. We know that's not enough. N is 8. We, of course, need more. And each of the slices is a little bit different. That means that area has to be defined for that sample point. Yeah? X sub I, and we know how to compute X sub I. But in general, area of the cross-sectional area times the thickness, base times the height is just the volume of a cylinder. And now, yes, we would like to add all of them. That means sigma is involved. Yes, sigma is. I'm just trying to derive the formula. Then we will get the formula and we will be just using. Okay, that means this is the addition. And now, can you remind me how we can make this approximation perfect? Because we can see when I cut just by 8, like dividing by 8 slices, that's not a perfect fit. Yes, perfect fit to that line. We have like, we have just, not good. N has to be like big, has to be infinity. That means we will say that I type, yes, we want N to be infinity. We want infinity many of these slices because then they're gonna be so thin when we think about like, yes, height, it will be like almost zero. But that's what we need. We need the infinity, and this is limit. And can you also help me? Limit of the sum. How we can simplify? What is the limit of the sum? Adding infinitely many items. Summation means adding, limit, of course, n goes to infinity. How we can replace limit? It's just the integral. That means we will integrate just the cross-sectional area, and we know that dx delta x becomes dx. And since the x sub I depends on a and b, that means this is the limit, definite integral. That's what we need for this section. In order to get like the shape, the volume of the, let's say, weird shape, we have to cut it, okay? We have to look at the cross-sectional area and just integrating. Okay, sometimes the cross-sectional area is nice, like maybe a circle, maybe a square, maybe triangle, maybe half of the circle. We will see. We will have today, and that's when we have to just defined in terms of the independent variable, which is dx x. We have to create cross-sectional area. In this picture is that shape, which is a little bit weird, but hopefully we will have, yes, better shapes. And one more time, we have to get that area in terms of independent variable. And what is the independent variable? In this situation is x, is changing from a to b. We can always think like whichever interval, whichever like line segment we slicing. Then if we slicing x-axis, we will integrate with respect to x. If everything is like in the vertical position and we slicing like with the horizontal lines, then we slicing the y-axis. Everything will be in terms of y, even the limits. Okay, that's it. And let's look at this one. Oh, that's actually nice. The apple. Yes, what's the volume of the apple? We may slice it, yeah, and we can see this will be, one second. Okay, we can see this will be the thickness of each slice delta x. And actually, this is also interesting. Let me put x and y. And how we can set up the integral that will represent the volume. We have to integrate the cross-sectional area, which the cross-sectional area, if we take this one slice, what do you think? What we can say? What is the shape of the cross-sectional area? I think I am actually a circle. We can say it's a circle. That means we can that's really good. Let's say pi r squared. And now my question is, did we slice x-axis or y-axis? Oh, that's mean actually this is actually y-axis. That means this will be delta y, this will be dy. Everything has to be with respect to y. And we can say from, my 0 is from 0 maybe to a. From 0 to a. But what is important, that formula, the area of the circle, we have to rewrite in terms of y, because everything has to be in y. That means if this is circle, I don't know if I can draw it. Yeah, it's like a circle. That means we will need that radius r. Yeah, I don't know, this point and maybe this point, this will be a radius. That means this is maybe like a challenge. We know the shape, we know the formula for the area, but we still have to rewrite in terms of that particular variable. In this situation is y. Okay. That means this is still good, yes, but we may be careful, like which values we have, which like variables we're looking at. Okay. That's it. Just integrating cross-sectional area. That's it. And now Oh yes, I have actually this one in terms of y, the same thing. It's not an apple, but something similar. And that's we can see. It's a little bit more details, but we don't have to be exactly like precise. I mean, we will not define, we will not compute this. We have to be always precise. But what I was saying, we will not compute through the definition. We will just evaluate the integral. But what we have to find out, we have to find out the area of the circle here, for instance, with the radius, because that's the formula which involves radius in terms of y in this situation. Okay, so now let's look at first example. Okay, that means probably this question we can solve like less than a minute, because we know, I hope we remember the formula for the volume of that pyramid. But we will use the integrals, okay? That means calculate the volume V of a pyramid of a height 12 meters, whose base is the square of the side 4 meters. That means 4 by 4. Okay, excellent. Actually, do you remember the formula for the volume of the pyramid? It's because pyramid is not exactly a cylinder. Yes, of course, it's a pyramid. We still need the area of the base times the height, but since it's like a cone or pyramid, we will have just 1/3. Okay, that's we have 1/3 area of the base. What's the area of the base? Base is the square 4 by 4. 4 squared, right? And the height, what is the height of this? I think height is 12. Okay, can we compute this? 16, and we can simplify this. It will be 64. Okay. And let's maybe add units, meters cube, because volume is cube. Okay, that means actually we did, but no. We will use our integration. Okay, we will use integration because we would like to get the use of the integrals, just in case if the shape will be totally different. But this is good to know the final answer. Okay, that's my question like this. I think my second example, it's more like exam type. I mean, this one is also, yes, this one is also. That's in what we will do. We have this shape. Let's say we have no idea what's the volume. We know that we may start slicing. That means I'm taking this pyramid and I'm slicing. Yeah? That's you can see. I mean, in this situation, I can even call x's because I didn't really place that pyramid in the xy plane. Okay, I didn't place in the xy plane. That means even if the vertical, I can still call it. Y. 1 second, because I have some. Okay. Okay, that's mean what we will do, we will slice it, okay? That's mean you can, and what we did, I'm not gonna mess up the picture, we will slice it from the bottom, from 0 up to 12, okay? That's when we know the limits. And this is one of this slice or slab, I can call it. Okay, that's one of them. And the notations actually are really nice. And we can say this slab is, because we're going from 0, at some point x sub I, yes, at the height x sub I, because that's my sample. Okay, that's me now. Actually, I can maybe use green. Volume of this one slab will be, because now that one slab with the thickness delta y. Okay, we can imagine it's really slim, but it has a thickness. It's a cylinder. That means the volume of the cylinder, area of the base times height. Let's maybe use small h. Okay, that's mean, and we can call it, which we have it, that it's still a square because each of them will be square with the size of the side will change, yes, will get smaller and smaller. Let's call it S. That means this is S squared as the area of the base, because that's S, we can see S, and height is that thickness, delta Y. Okay, area of the base and thickness, height, delta Y. Okay, that's me now. Can I keep that S? Let's keep it. Let's keep that S because we have to find that S in terms of Y. Let's maybe find the S in terms of Y. Because I was thinking if we would like to have the volume of everything, but we need Y because we need the sample point. Okay, let's rewrite. Okay, the first exercise. Let's rewrite that size. Yes, I mean the site, the size of the site, the length of the site. Let's define. Now it's called S, but we have to find out the formula in terms of Y. And we see lots of nice, yes, we see lots of nice labels because I took it from the textbook. Okay, that's what we have. Let me look. This is a middle of this, and I can create, I think let's see, let's touch here because I would like to see a couple of triangles. This and this, and this will be the right. Okay, that means the red, okay, the red, I will get two triangles, similar triangles, and from the ratio, we will get the formula of S in terms of Y. That means please help me. The height of this red triangle, actually we have the labels on the, because we decided to call Y from the bottom, okay, Y from the bottom, that means that height of the red triangle will be 12 minus Y. Do we agree with this? From the entire, we can see from the entire 12, we subtracting Y. Sample, Y sub Y. Okay, thank you. That means this one is 12 minus Y sub I, because it's the sample. Okay, excellent. Now, can you tell me how I can define the base of this triangle? Base. Do we see it's a little 3D, it's a little, with respect maybe to S. That base of the triangle is half. Perfect. Half of that S, yes, because we can see it's kind of like half of the base. Excellent. And we don't need the hypotenuse now. And now I will take the big triangle, the entire height, the entire half, and I don't know if I can, okay, this is, no, my drawing. Oh, no, that was good. This is, and the hypotenuse will be here because the blue one is the edge, okay? And this is also the right. That's we will have another triangle with the entire height. And can you tell me the base of the purple triangle? Yeah, similar triangles. The base is also half of the total base. That means it will be half of the 4, 2. Yeah, makes sense. This is 2, which actually we haven't. Actually, we have that on the other side. I just draw it on the opposite side. Okay, that means now we have a similar triangles. Let's get the ratio. We can say height over base, height over base. Perfect. And we can solve it for S. And that will be the size of the site of our like cross-sectional area of our slice or slab. And then we can put, we can create a integral in a second. Okay, that's what we have. We can have 6, 12, 1/2 S, 6 times 3S, 12. Okay, that means S is 12 divided by 3, 4, and Y sub I divided by 3, I can keep it 1/3. Okay, that means now we are good. we can say the volume of this one slab will be S squared delta Y. And S is defined as a 4/1/3 Y sub I. Perfect. And now when we want all of them, we can have just summation from 1 to n. 4, because we can see we have Y sub I, Y sub 1, Y sub 2, like for every single level, squared delta Y. And now, and this will be still approximation. Now, when we take infinitely many of those from 1 to n goes to the infinity, 4 minus 1/3 Y sub I delta Y. And now, limit of the sum is a definite integral, 1/3 Y. Now we're dropping the I. We know that the integration will take care. Oh, this is Y. This becomes dy squared. And limits of integration, because that sample point Y sub I, we have to indicate how far is changing. That means what limits of integration you can suggest. From, of course, from the bottom 0 up to the top, the tip, the vertex 12. Thank you. Okay, and I believe that integral, we have to get the answer 64. We can maybe try. Okay, that means first of all, we have squared. We have to expand it, okay? Because we may use the U substitution, but let's just expand. Like FOIL, 4 minus 1/3 Y times 4 minus 1/3 Y. That's we will have 16 minus 2 times 4 times 1/3 Y and plus 1/9 Y squared. Okay, and now we have to integrate 16. Integral of 16 dy will be 16y. Integral of 8/3 y will be 8/3 y squared over 2. We can simplify. And this one will be y cubed over 3 times 9, 27, from 0 to 12. Oh, when we substitute 0 is 0. When we substitute 12, maybe you can check later, but we know that the answer is 64 cubic meters. Yes, I just use, but that's what we need. And for instance, on the test, I might ask you for this. Yeah, oh, I cross it there, limit. Like set up the integral that will represent the volume of that pyramid. That means this is this. Okay? Let's do the same one a little bit quicker. Oh, 64. Okay, let's look at this one. Okay, that's the same thing. Now we have no picture now. Consider the pyramid with a square base, good, of the size length 10 centimeters and the height 15. Okay, part A, slice the pyramid into a horizontal slices, each with the height delta x. I mean, now it's maybe a little bit different because we're still slicing theoretically the y-axis, but we will label x everything. It's still okay. Because we're not exactly in the xy plane and we're not using directly like a formula of the function. Okay, delta x. Now, find approximate volume of the slice, that is vertical distance, that's also important, that is vertical distance x sub I centimeters from the tip. Do you see this one? This one, we had vertical distance. Yes, that slice, that slab was y sub I from the bottom. Now we have to label from the top. Okay, let's come back. From the tip of the pyramid. The only variables in your answer should be x sub I and delta x, which actually, let's come back. This is, okay, just one. Yes, they want one. That means this is the answer. I can even call it part A. We don't have it part A, but that's what it is. As we can see, s squared delta y. Now we will have everything in terms of x, but we have to be precise for the picture. Okay. And now write a definite integral that gives the volume of the pyramid, and we don't have to evaluate. We can get the answer. Okay, that's it. Let's start. What you will do on your test. You will draw a pyramid, hopefully. Square base. I will draw the diagonal because the intersection of the diagonal will show us the height. And now vertices here, here, and here. Okay, perfect. This is 10 by 10. And the height, how can I get the height? Technical drawing, I don't know if you had technical drawing, 15 centimeters. Okay, okay, we good with this. Now, we will get, yes, we slicing everything and I will just draw one slice, one slab. Let's say here, 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 and here. Beautiful. Okay, and now, yes, I can even draw that triangle because we will probably need this triangle. Oh, this one is a little bit better. Okay, but this height, or maybe that slice is placed xi sub I unit from the tip. That means this distance. Okay, this distance is x sub I. Okay, and of course the thickness, is this saying the x is a vertical? Yes, kind of, but we don't, because we, at the moment, we don't even have to think like, yes, I know like x-axis, y-axis, but yes, vertical axis is just x. Yeah, like we don't even have to really involve x, y, because we don't really, as I said, we don't really use the function which depends on x or y. We just have the labels in terms of x. That means this is a nice example to it's taking us away from the like x and y, because no function is involved, just our label. I can even, instead of that x, you can label y. You can say everything it's y. Delta y sub I, delta y, y, I mean, y sub I, you can call it y, or you can call it even different variables. But yes, Reese, the answer for your question is yes. Yeah? At this, yeah. Yes, we don't have to think for this pyramid question, we don't have to. We will do in a minute, like the next examples, and then we will see, because we will use, yeah, really like XY connection, XY like Cartesian coordinate, and then we have to respect everything. This one is just a label, yes, yeah, but good question. Okay, that's me now. Let's see. Volume, part A. Okay, that's me again. Volume of just one will be area of the base times height. It's s squared times delta x, because that's the thickness, which I suppose, yeah, that's the thickness, delta x, and the size is s. Okay. We need s in terms of x. Let's build right triangles. Okay, similar triangles. Okay, that's we have this purple triangle, which we know that the height now is just x sub I, we can see, and the bottom is half of the s, because we can see it's half of that side. Okay, and then we need a big triangle. Let's maybe say blue, 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 and that hypotenuse. Okay, that means the blue one is 15, the height, and half of the bottom, which is 5, the side. Okay, let's get the ratio. That's we will have x sub I over half s, height over base, height over base. Okay, that means x sub I equals to, this will be 3 times s. Okay, I mean 3 times half of the s, 3 halves s, and then s will be 2/3 x sub I. That's what we wanted. S in terms of the variable. That means 1, s squared times delta x, 2/3 x sub I. Let's make, yeah, I can actually leave it. I can leave it like this. That means actually that's part A. this is part A. We have the volume of one slice, okay, of one slice of that, yes, I mean one slab, one slice. Now we can start building a definite integral because all of them, volume of volume of the entire, yes, let's say approximately, that means this is just one. It will be the addition of all of them, x sub I squared delta x. I is from 1 to n, and the perfect will be with n from 1 to n being infinity. Yes, we can see the same thing, and we can write the definite integral. Okay, we can write a definite integral. It will be just 2/3 x sub I. Oh no, we don't need I because the sample point, the limits of integration will take care. This becomes dx. And what are the limits of integration? The limits of integrations are like whatever like we slicing. That's when we did slice from 0 to the entire height actually from 0 to 15. Okay, this is answer to part B. Definite integral we don't have to evaluate. Which actually you can tell me the answer. Let's maybe use, let me write here. Volume is 1/3 area of the base times height. Yes, area of the base is 10 squared and height is 15. 10 squared is 100, 15 divided by 3 is 500 meters or centimeters cubed. Okay, that means this answer is, of course, 500. Actually, am I right? Divide by 3, 5 times 100, 500. Okay, but what we need that integral. That means probably, yes, again, on the test, I will ask you how to set up the integral. We can say it's just, we have to just think about the cross-sectional area, just integrating cross-sectional area. Always think like what we're slicing, just the length. Okay, let's keep working. Oh, okay, let's just set up. That means this is nice example. Also, compute the volume, but we will just set up, okay? We will just set up, I mean, we will see. Compute the volume V of the solid in the figure, whose base shown at the bottom in the figure, we actually have it. Base is the region between the parabola, y equals to 4 minus x squared, and the x-axis. Actually, that gray part, we can see that's the base. That's the base. And on that base, we actually creating half of the circle, semicircle, whose vertical cross sections are perpendicular to the y are semicircles. Yeah, that's, can you imagine? I didn't draw. I can draw maybe the next question, but I didn't. I mean, we can still draw it, right? We can like imagine, oh, I don't know if that's good color. Half of the circle. And that diameter is, of course, bounded. Oh, I'm a little bit, oh yeah, not bad. Do you see my 3D? It's actually, yeah, it's quite, yes, quite good. That's me. We have to now, yeah, we have to now imagine. Now, yes, now we're building this half, when I slice, that's me. Now it's important, X and Y, yes. Actually, what we're slicing, in order to see this half of that circle, what we will be slicing, x-axis or y-axis? Are we slicing x or y? We're slicing y-axis, really good. That's we know we can even set up right away because we just need cross-sectional area with respect to y because we're slicing the y. And actually, this is half of the circle. Pi r squared over 2 dy. Please tell me, I can skip all of the limits, all of the sigma, okay? Because we did the 2 examples, it's fine. Please tell me the limits of integration. Where is the beginning of my slice and where is the end of my work? Y-axis, yes, that means, do you see the limits? Yes, between 0 and 4, because we can see that's 4. I can maybe remove this. That was not bad drawing. Okay, that means that's almost everything. However, we need R. We need a radius of that semicircle in terms of Y. We know Y in terms of Y because everything is in terms of Y. That means this is, yes, we can see that's R. And we may say this is R. I have the labels, I know, but normally what we can do, let's maybe look at this. If that's the parabola for, this is Y, this is X, that distance will be a radius, correct? That's the radius. If I do the prediction, this is -2 and 2. If I like project on the x-axis, it's actually the distance from the y, from the 0. That means radius is theoretically x. As we can see, x is of course between. But that radius depends on that curve. It will be here, it will be here, here, wherever I slice. That means depends on that curve. But since the radius is x, we need to solve that equation for x. That means this equation, where I can write, it is y equals to 4 minus x squared. We just have to solve it for x. And that x, because I can draw it one more time, this is radius when we project, because it's parallel to the x-axis. That means it's the same distance as from 0 along the x-axis. Okay, that means let's solve it for x. X squared will be 4 minus y, then x is plus or minus square root of 4 minus y. Since we are in the first quadrant, we can just take a positive. Okay? We even squaring, that means it's not a problem. Okay, that means volume. Let's set up volume between 0 and 4, pi over 2, radius squared. And radius is square root of 4 minus y. Yes, because that's square root of 4 minus y. I just draw it here. And we may put pi over 2 between 0 and 4. Square root squared will be gone. It's just this. So nice and easy, right? And now we can even, no, I can leave it for you. You can integrate because it's just integral of 4, integral of y with respect to y. Okay, because let's set up the other one. Okay, but we can see how nice, really nice. Okay, let's look at next one. Yes, oh, the answer is 4 pi. You can try. I know that you can try. I can leave it this one for you. Okay, it's also nice. Just the circles, because we actually know the formula. Do we know the formula for the volume of the sphere? Who remembers the formula of the volume of the sphere? That's actually using a definite integral. Yes, 4/3. I think it's 4/3 pi r cube. Okay. Yes, 4/3 pi r cube. And r, yes, r is the big R. That means setting an integral and solving this, we're supposed to get that answer. Okay, but you will just integrate the cross-sectional area. Please tell me, with respect to y or with respect to x? Actually, the picture is suggesting, yes, that means the picture is suggesting that because this one is so symmetric, we may even slice it the y-axis. But I think it looks like we did slice the x. Okay, that means with respect to x, And it's basically pi r squared. But we have to get, yes, in terms of x. Can you tell me the limits of integration? The limits of integration, where are we starting, where are we ending? I know, yes, it's just from negative r to r, from negative r to r. Okay, but you can figure out, it's almost everything on the picture, but you can try, please, yeah, integrate. I did solve it for you. Okay, now I want, yes, you can. Let's do this one. Okay, oh, 1 second. This one is, because I have, okay, let's do 5. I have a picture, but it's, yeah, no, let's draw it. That's me now what we have. Let's set up the, let's find everything. The base of S is a triangular region which vertices 0, 0, 1, 0, 0, 1. Cross sections perpendicular to the x-axis are squares. Find the volume of that solid, of this solid. Okay, that means first of all, we will have x and y and 0, 0, 1, 0, and 0, 1. 1, 1. Okay, that's we have that triangle. That means that's the base. And on that base, we have to build, like we have to put a squares. Okay, perpendicular. I can put square, square, everywhere will be squares. But let me maybe, how can I draw? Let's say X, let's say Y, let's say triangles. And then I can build, that's the square. That's this, oh, not square, square, square. Yes, can you imagine that solid? My solid is, and maybe the last one, square, the small one. Okay, that means it's kind of like, yes, we will have smaller and smaller size of the base. But definitely this distance, let's say x sub I, that distance is actually the side S. Yes, that's S. The size of the side of that square. This one, I don't like this one because it's supposed to be more square. Okay, that means volume will be cross-sectional area. Cross-sectional area is just the square. Okay, that's cross-section, integrating cross-sectional area with respect to x, because we can see we're slicing x between 0 and 1. Let's say s squared. And now, how we can find the s in terms of x? Now it's there. That side, I can maybe use different color, s. Okay, s, when I take this line segment and project on the y, it will be like a y value because it's changing, yes, with respect to y. I mean, it is y, we can get the formula with respect to x, but it's because it's like, it's a vertical line. That means I can project and it's a distance from 0, like going up. That means that's the y value. All right, that means s is y. That means what will be nice? It will be nice to find the formula of this function that goes through, because then we will have a formula y equals to equation of the line, which goes through the point 1, 0 and 0, 1. That's it. What is this line? mx plus b. That will be the equation. Slope is -1 and y-intercept is 1. That means y is basically negative or x plus 1. That's it. And that's the s. That's we can see we have to keep really like the x and y is important. S squared means -x plus 1. That's the s, the size s. And we can even flip this for the better. And we still have to FOIL 1 minus 2x plus x squared. And now you can integrate term by term. And I think I have the answer. Answer is 1/3. Okay. Okay, that's it. I have more examples, but I can leave it for you. That means please remember, always get the cross-sectional area, and we will always tell you what is the cross-sectional area. If it's the square, is the formula for the area of the square, if it's circle, if it's half of the circle, and then try to rewrite in terms of the correct variables. If we're slicing x, everything in terms of x. If we're slicing y, everything in terms of y. Okay? That's why I have two more, but you can, I solve it for you. I can leave it